Hello, my name is Jean Rebecca Lee. I'm a research scientist at INRIA, which is the French National Institute in Computer Science and Applied Mathematics in the Paris region. I would like to welcome the audience to the invited talk of Section 14, Mathematics of Computer Science, on Sunday, July 10th, for the next 45 minutes. It is my great pleasure to introduce our speaker, Professor Muli Safra. He is a professor of computer science at Tel Aviv University in Israel. His research is in the mathematics of computation. The title of his talk is Mathematics of Computation Through the Lens of Linear Equations and Lattices. For technical reasons, we will not be able to take questions. So now I give the floor to you, Professor Safra.
Good afternoon, everyone. I'm Muli Safra, and I'll be talking today about the mathematics of computation via the lens of linear algebra and lattices. The plan of the talk is to introduce some computational problems and view them as a special case of linear equations, then generalize those problems over lattices. Some of the problems I'll be mentioning are the unique games problem and the 2-to-1 games problem, which are prominent extreme examples of the hardness of approximation, or as the area is called, PCP. I will demonstrate that these problems are special cases of the closest vector problem and the shortest vector problem, either over error correcting codes or over lattices. The mathematics involved in analyzing the computational complexity of these problems require some deep mathematics, such as the Minkowski theorem and what is referred to as a reverse Minkowski theorem. All through the talk, I will be considering the computational complexity of these problems, as well as the positive implications of showing a problem infeasible. So let us define the computational problem of solving a system of linear equations. We're given m equations over n variables, and our goal is to find an assignment to the variables that satisfy all equations. Formally, the input comprise an m by n matrix M specifying m linear sums, and a target vector T specifying the value those sums are expected to be equal to. The computational problem is to find a vector x so that m times x equals the target vector t. So how efficiently can this problem be solved? With this audience, nobody will be surprised that the problem can be solved very efficiently, in fact, in linear time, via the process that is referred to as a Gaussian elimination. One takes one equation and one variable, uses the equation to represent the variable as a linear sum of the rest of the variables, thereby getting rid of one equation and one variable. One is left with a smaller problem and could proceed in the same way for the next variable or the next equation, until eventually the variable are assigned a value satisfying all equations if such an assignment exists. It would be easier for our purposes to define these problems over error correcting code. So let us first define what an error correcting code is. An error correcting code is simply a subset of all vectors of dimension m over some field f, some finite field f. F to be the m can be considered as a vector space, and therefore if C actually form a subspace of that vector space, we refer to such a code as a linear error correcting code. The dimension of the subspace is denoted by n, which is an important parameter of the code. The code can be used to transfer messages of length n by messages of length m, so this is a loss in terms of how long the messages are. However, if not too many errors have occurred along the transmission, we would be able to still decode the transmitted message. The other important parameter of a code is its distance, d, which is the minimal distance between two vectors in the code. The distance we will be using is the Hamming distance, which is the fraction of indices on which the two vectors differ on. Since the code is linear, we can measure the distance from the vector 0, which makes the analysis much easier. A linear error correcting code could be represented by its generating matrix. It's a matrix M that takes vectors of size n and translates them into vectors of size m. The code C is then simply all the vectors of size m that can be represented as a product of m times a vector of dimension n. To encode the message x, which is the vector of dimension m, by the code, simply transmit the vector m times x, which is indeed a vector of dimension m. The vector at the other side of the channel could be a little corrupt. Therefore, we might be receiving a general vector t, which is a vector of dimension m over the field f. Nevertheless, as long as the fraction of errors is smaller than half the distance of the code, there is a unique vector x so that its distance from the vector t is less than half of the distance. Finding that vector x is what we refer to as the decoding of the message. We can visualize an error correcting code as a sparse set of points in some metric space. In this case, we use the Hamming metric, and as you can see, the set of red points is a sparse set in that metric space. When a message is transmitted, some errors may occur, and let us now figure out what does it mean to decode such a corrupt word. We receive the vector t, and then we look at the Hamming ball around it of radius 1, and as you can see, there is no original vector in the code that is in that ball. Therefore, we increase the radius of the ball to 2, and then we find out a vector in the code that is within distance 2 from t, and it is unique. We thus conclude that that vector was the one transmitted over the channel. Let us now visualize the distance of the code. As we said, we might as well look at the closest vector to the 0 vector. So if we look at the 0 vector and draw a ball around it, small radius, we can increase the radius. And then once we get to a ball of radius 3, a Hamming ball of radius 3, we see that some other vectors in the space is in that ball. And we conclude that the distance of the code is 3. So we are now ready to define the closest vector problem in such metric spaces. The input to the problem is a matrix M. C is all the vectors that can be represented as m times x for some x in f to the n. The input also include a target vector t. The computation problem is to find the vector in the code that is closest to t. That is, find an x so that m times x is closest to t. This is clearly a generalization of the decoding problem we just discussed. Let us go back to our system of linear equations and the problem of finding a solution satisfying them. Let's amend it a little and require the algorithm to figure out if there exists an assignment that satisfies almost all of the equations. Namely, is there an x so that the distance of mx from t is small, say 1%. This problem is clearly a special case of the CVP problem we have just defined. We are given a matrix M and a target vector T.
When we say decision, we mean that the purpose of the algorithms is just to decide whether such an assignment exists and not actually find it. This problem at first glance may look, in fact, easier than the original problem that asked us to find an assignment that satisfies all of the equations. However, this is clearly a wrong assumption. Looking at it a little, you can see that it is actually quite hard to figure out which 1% of the equation to give up on. Only then we can apply the Gaussian elimination algorithm. By just changing the requirement of the assignment satisfying only almost all of the equations, we have made the problem much harder. In fact, this problem is known to be NP hard. Therefore, if you find an efficient solution to it, you will be able to solve efficiently all problems in NP. Such an algorithm will not only change our view of computation, but in fact might change our perspective of humanity.
Hopefully convince you not to tackle such hard computational problems and not to try to find efficient algorithm for them unless you think that P is equal to NP. Let us define some problems that are easier computationally. In particular, let us try to find approximation version of these problems. The input is just the same, a matrix M and a target vector T. The computational problem, however, is much less strict. The algorithm must accept all such inputs in which there is a vector in the code represented by M that come close to the target vector T within epsilon Hamming distance. This is just as the same as the previous problem. The algorithm, however, needs to reject only inputs so that there is no vector in the code that comes even close to the target vector. In these settings, as written here, the algorithm must reject if all vectors in the code agree with the vector T on less than epsilon fraction of the indices. What happened on the rest of the inputs? The algorithm could return any answer. It could either accept or reject such an input. Formally, we write it as a promise problem, where the input is promised to be in one of these cases, either the accept or the reject. We call these problems gap problems, there is a large gap between the accept case and the reject case. And indeed, this problem is a special case of the CVP gap problem. One might have hoped for this problem to be efficiently solvable. However, due to a revolution that the math of computing field have gone through in the last 3 decades, namely the PCP characterization of NP, we now know that this problem is still NP hard. Now that we know that gap CVP is NP hard, therefore, no one would try to come up with an efficient algorithm for it unless they believe that P is equal to NP. We can look at easier problem. And the most prominent case is the unique games problem. The input is still a matrix M and a target vector T. However, there is a very strict restriction on the matrix. If we look at the set of equations, we see that every equation requires the difference between two variables xi and xj to be equal to bij, some element of the field. So this is obviously a special case of gap CVP, in which the equations are very strict. It is therefore could only be easier than a general problem, as we might be able to utilize that restriction. The goal of the algorithm is as before. It must accept all input in which there's an assignment that satisfies almost all equations, and it must reject all instances in which no assignments satisfy even an epsilon fraction of the equations. And again, it is promised that no input falls in between these two cases. Therefore, this is a gap problem. This problem could be easier than a general case of gap CVP, as one might be able to use a strict limitation on the type of equation that we are given. So what is the complexity of the unique games problem? This is the most important problem in this field of PCP. It could be the case that the unique game problem is NP hard, although I would doubt that this is the case. There are many attempts to give a real sub-exponential algorithm for the problems, but they could not go beyond some slightly less than pure exponential complexity. And these attempts were abandoned after some theorem that I will mention later show that this is unlikely to be possible with current technology of algorithms. The third option that we should consider seriously is that this problem is in between. Namely, there is no efficient algorithm for it. Nevertheless, it is not NP hard. Let me point out here that resolving this problem, this open problem, whichever of these 3 ways, or if you can find another way, would have tremendous implications on the entire field. Still, serving these implications is beyond the scope of this talk. Let us then define what a lattice is. The field we will be working on from now on is the field of real numbers. In particular, we can look at Rn and think of it as a group with addition as the operation of the group. It is then the case that any discrete subgroup of that group constitutes a lattice. We will say that the lattice is full rank, and from now on we will only be dealing with full rank lattices if the span of the vectors in the lattice is Rn. An alternative definition of a lattice is via a matrix. So we have an n by n matrix, and we look at the matrix multiplied by integer vectors of dimension n. Or in other words, we look at all the linear integral combinations of the column of the matrix. These will constitute a discrete subgroup of Rn. For example, z to the n is a legitimate lattice within Rn, but if Q is an infinite field, then Q to the n is not, as it is not discrete. A very important parameter of a lattice is its determinant, and one way to define it is the determinant of the matrix M. An interesting observation is that if we take a ball of radius r and let r tend to infinity and consider the volume of that ball divided by the number of points within the lattice and the ball, then this approaches the determinant of M. One of the crucial questions that we will be asking, but the answer is not yet clear, is how fast this ratio tends to the determinant of M when R grows. In other words, how large should R be when this becomes very close? Another set of very important parameters for a lattice is what is called the successive minima. Let us just define the first one, lambda 1, to be the length of the shortest vector in the lattice. These two parameters may suffice for our discussion here, but there are many more parameters and interesting properties of them that are beyond the scope of this talk. A lattice is therefore a sparse set of points within Rn. Being sparse, we can legitimately define the closest vector problem. Let us visualize it here. We have a space of dimension 2. We have M1 and M2, which are the columns of a matrix, but also a basis for Rn. The set of red points are generated by integral combinations of M1 and M2, and this is indeed sparse. We have a target vector, and we are looking for the closest vector to that target vector. We may assume from now on that the metric that according to which we measure distance is the L2 norm, and here we have an L2 ball around T that at some point contains a vector from the lattice, and this will be the vector closest to the target vector. So the input to the computational problem that we consider is, as always, a matrix M and a target vector T. And the search problem is to find the closest vector to T, to the target vector in the lattice, which means find V, which is a vector of integers of dimension n that minimizes the distance to T, so mz times minus T is the smallest. One should notice that the same lattice could have many bases, many matrices that span it. For example, if you look at the lattice at the top of the slide, you can see that there could be a much nicer basis for the same lattice. Still, the inputs specify one particular basis, and the algorithm must compute the closest vector according to this basis and not according to a basis of your choice. Time has come to consider the rich area of computational complexity of approximation problems over lattices. Depending on the ratio of approximation, these problems could be NP-hard, could be approximatable by an efficient algorithm, or could be otherwise. Let us try to see what we have here. So first, in terms of NP hardness, SVP is known to be hard to approximate to within that strange ratio. This is due to Michancho and Court. With respect to CVP, it is known to be NP hard to approximate to within a ratio n to the 1 over log n, where n is the dimension of the lattice. This is a joint work with Dinur, Kindler, and Raz. If one is interested in approximating any of these problems, SVP or CVP, to within a ratio of square root of the dimension, the problem, somewhat surprisingly, is in a class which is referred to as NP intersect CoNP. It suffices to know that if a problem lies in that class, then it is highly unlikely to be NP-hard. This gives us a natural bound as to how far we can push NP-hardness for these problems. These are due to Goldreich and Goldwasser and Aharonov and Regev. The most heroic result here, one that sparked all of our interest in computational complexity of lattice problems, created some beautiful mathematics, and also has tremendous applications in cryptography. In fact, it transformed the field, is due to Aitai from the mid-90s. It says the following. Suppose you have an efficient procedure, an algorithm, that solves SVP on an average input, an input that is drawn from some distribution. You can use that efficient algorithm to solve the same problem in the worst case, meaning to solve it on any given input. This is crucial when trying to apply such results to cryptography, as we will see in the next chapter of this talk. A somewhat more digestible proof of the same theorem appears in Michancho and Regev from the early 2000s. As to approximation algorithm for these problems, there is a most amazing algorithm by Lenstra, and Lovas from the early 80s, which approximates SVP to within a ratio exponential in the dimension. This might seem like a weak ratio of approximation. However, this has applications in many areas, especially when a dimension is rather small. This may be one of the more important algorithms in history. The algorithm was generalized by Bye-Bye to the CVP problem, and later Schnorr improved it and figured out how to get a slightly smaller factor in the exponent of this problem.
It is important to note that despite those quite amazing results, there's still a whole range that lies here for which the complexity is not known. And resolving any of this or showing some connection between those problems to other problems will be just amazing.
Let me now try to clarify the positive impact of proving a problem infeasible. Just assume for a moment that P is equal to NP, and observe that under such an assumption, there is no cryptography. An eavesdropper could listen to the exchange between two parties that share a common secret, guess in NP what is a secret, and verify that indeed that is the secret corresponding to the exchange. If P is equal to NP, then this process can be carried out efficiently, and therefore any cryptographic system would be broken efficiently. It is therefore the case that any cryptographic protocol must assume, for purpose of proving security, that some problem is hard. After 4 decades of not being able to improve on the LLL algorithm, it is safe to assume that SVP is indeed hard. Still, for cryptographic applications, we need to assume that the problem is hard on average, namely on an input chosen randomly from some distribution, as that is the way keys are chosen in a protocol. This is the reason for the tremendous impact of Itai's result, who show that SVP on average input is as hard as SVP in the worst case. Namely, if you have an efficient algorithm for SVP on average, you can compute SVP on all inputs.
To clarify the distinction between worst case and average case, let us be a little more precise. The worst case complexity of an algorithm is considered according to input on which it performs worst. So in order to solve the problem within some complexity, it must solve it on all input within that complexity. In contrast, in average case, we measure the complexity according to an average input. We assume some distribution over the input and take the average of the complexity of all inputs. This means that the algorithm might do some strange thing with small probability, like return the wrong answer or not stop at all. This is still legitimate. Obviously, this is much easier to get than the worst case. When it comes to cryptography, we must assume infeasibility in the average case as the secret key is drawn from some distribution. We must assume that when we draw some key from that distribution, the problem is hard on that key, at least with high probability. This is where lattice come in very handy, as almost the only source for worst case to average case translation relate to lattices as the result of Itai and later Michancho and Regev. One of the most fundamental results regarding lattices is due to Minkowski, and it's a convex body theorem. It states that if you take a convex centrally symmetric body whose volume is 2 to the n times the determinant of a lattice, then it must contain a non-trivial vector in the lattice, namely a vector different than 0. This is tight as if we take the grid and look at the open cube minus 1, 1 to the n, then its volume is nearly that volume. Still, it does not contain any vector in the lattice but the 0 vector. This could be extended as follows. Let us assume from now on that the normalized
the lattice so that its determinant is 1. Then, if we take a ball of radius square root of n, it must contain some point other than 0 of the lattice. That statement was further extended to the following quantitative statement. It says that if we take a ball of radius r and look at the points that are in the lattice and are inside the ball, then their number is bounded from below by the volume of a ball of radius r over 2. The meaning of such a statement is that global density, namely the determinant is small, must imply some local density, meaning that there are many vectors in the lattice that are close to the vector 0, to the origin. A reverse Minkowski type theorem considers the other direction. Let us state it simply as saying that we would like to bound from above the number of lattice points within a ball of some radius. So here is a statement. Suppose we look at a radius r, which is roughly square root of n, and then consider the set of points of the lattice that are within that ball and look at the number. The number would naturally be the volume of the ball divided by the determinant of the lattice. So the statement here says that it is enough to multiply that bound by square root of n to get a real upper bound on the number of points. The only problem with the statement is that it is only proven for a stable lattice, where a stable lattice is a lattice so that every sublattice of it has a large enough determinant, at least of size 1. And here's a conjecture that such a statement is true for a much more general class of lattices. Never mind the specific class of lattices that I mentioned here, just extending the statement to a larger class of lattices would be fantastic. And let me point out that this is beyond the scope of this talk, but such a statement would have tremendous impact on the complexity of these problems. Let us start with open questions and research directions regarding the complexity of classical approximation problems. The most prominent one is unique games problem. Now, this problem could be NP-hard, but I personally would doubt that. It is also unlikely to be efficiently computable. So, as I mentioned before, there's a third option, which is that it is neither. Now, how would you go about proving such a statement, or at least given a good evidence to that effect? The most natural way would be, I think, to reduce it to a lattice problem, one that we know that is in co-NP. Showing that unique games is in co-NP is a very strong evidence to the fact that it is not NP-hard. For the second direction, let me introduce a new problem, which is the 2-to-1 games. It is quite similar to the unique games problem. In unique game, we asked that some difference between variables xi minus xj is equal to some bij. In the 2-to-1 games, we allow the value to be either one of the two prescribed value, either bij or bij prime. Now, this problem was recently shown to be NP-hard in a somewhat celebrated result jointly with Koch, Minzer, Dinur, and Kindler. Still, there's a variant of this problem in which In the accept case, one expects an assignment that satisfies all constraints. Now let me suggest for this variant the possibility that the problem is in CoNP. It is obviously easier since the promise is stronger. We know that the assignment satisfies all of the constraints, and therefore the NP hardness does not apply here. It could be the case that it is in CoNP. Again, how would you go about proving such a statement? The only reasonable way I could think of is to reduce the problem to, say, CVP with a ratio of approximation larger than the square root of n, for which we know that the problem is in CoNP. Now, if that turns out to be true, then we may be able to base cryptography on the infeasibility of that 2-to-1 games. How would you go about showing that? If you can reduce the 2-to-1 games to a lattice problem and then apply the worst case to average reduction to show some average case problem to be as hard as a 2-to-1, you might be able to establish the security of a cryptographic protocol based on that hardness assumption. Going back to the computational complexity of approximating lattice problems, let us remind ourselves what is known. We know that the SVP problem is NP hard up to that ratio, while the CVP is NP hard to that ratio. We also know that within the square root of n ratio and up to there, the problems are in CoNP. We also know some algorithms that give rather weak approximation, but still quite interesting. Now, let's see what is plausible within those ranges. The first open question is whether CVP or SVP are NP hard to approximate up to that ratio, which we know that will not turn NP to be equal to CoNP. So these are ratios here. This is the most exciting research problem, although one should clarify that this problem is an open problem for more than 2 decades at least for the CVP ratio. I'm still willing to conjecture that this is true. However, it might require new technology and maybe a new look at PCP reductions. And here is a much bolder question, which is it possible that maybe SVP can be approximated efficiently by a quantum algorithm to within some polynomial factors? So this would mean that, assuming that we could have a quantum computer eventually, then maybe an algorithm similar to Shor's algorithm will be able to cover a much better range of these factors that could approximate SVP to within polynomial factors. Here is another grandiose project that unfortunately I don't have time to cover in this talk. With that, I conclude my talk. Thank you for your attention.
Okay, well, thank you, Professor Safra, for a lovely talk. I hope the audience members will have the opportunity to contact you offline or perhaps on the ICM Discord server for further questions and discussions. Take care and goodbye.